I am seeing a bunch of people have joined, so I think we can get started as some more folks trickle in. Hello, everyone. Thanks for joining this Wednesday afternoon. My name is Marshall Mutino. I'm one of the co-founders of Upstream Tech. And today we're going to be doing a pretty fun and unique deep dive with my colleague Laura Reed on hydro forecast. And through it, we're going to look at a basin. We're going to look at some forecasts, and it's going to be a great way to understand how machine learning can be used for forecasting streamflow. It was actually, in preparing for this, it was a pretty great exercise for us to see how in this specific basin everything played out. So to start, I'll introduce Upstream, tell you a little bit about hydro forecast, and then I'll pass it off to Laura. So first, about the team. We are just shy of 25 folks on the team. We're spread all across North America, and we're made up of team members with a range of different backgrounds, from software engineering at big tech companies to backgrounds in forestry, to working at federal agencies issuing forecast. So we bring the intersection of all of those disparate experiences together to build unique and technologically creative systems. And those two systems are Lens and hydro forecast. So Lens is a monitoring product that enables efficient remote and in-person monitoring using satellite and aerial imagery. And hydro forecast, which is what we'll be focusing on today, is a powerful and flexible hydrological model. And we'll talk more about that, obviously, in a bit. So in our work at Upstream, we work with a number of different kinds of organizations, from conservation orgs to land trusts to public sector agencies, and then also renewable energy utilities operating hydropower. Upstream Tech, as just a bit of background, is a public benefit corporation. So with all of our work, we track the impacts we're having. And for hydro forecast, we are looking at the breadth of forecasts we are producing. And for Lens, we look at the amount of conserved and restored area that we're monitoring. And so these numbers are growing, and we're really excited to see the new types of organizations we're working with every day. So back to hydro forecast. Again, I'm just going to give kind of a background of how the technology works and what's unique about hydro forecast, and then everything will become much more apparent walking through the example with Laura. But if at any point what I'm mentioning raises some questions, you have any gaps in what I'm talking about in terms of how the technology works or potential applications, you should be able to just drop questions in the chat, and we'll get to them as we go. So hydro forecast is it's a unique new way to forecast streamflow volume and a variety of water quality metrics. And what makes it unique is the way that we are combining all of the inputs. So a bunch of different weather forecasts from a bunch of different issuing organizations, satellite information from organizations like NASA, in situ data, and pulling that all together with the structure of what we call theory-guided machine learning. A little bit of extra color on that last point. Theory-guided machine learning is a way to apply machine learning in not a purely pattern matching way. You have two ends of the spectrum. You have trying to capture the natural world in physical equations, and you have trying to match a statistical function to historical data. We found that combining those two allow us to use the power of machine learning, which allows us to take those three types of inputs and constrain them in a way that gets to the accuracy of capturing the physical world in equations. And we get the best of both worlds that allows to tackle a number of different unique situations with pretty incredible accuracy. So what those unique situations look like, when we are looking at a basin for the first time, trying to assess if, how we're going to provide forecasts, we typically encounter 3 different situations. There's either no gauge, there's just no record of information. There's a gauge, but it has very intermittent signals. You know, there are chunks of the year missing, or there are entire years missing. Or there is a really great record up to today. Hydro Forecast, we've designed it so that it can tackle each of these situations. It can provide forecasts where there are no records. It can create historical hindcasts where there are unreliable records to fill in the gaps. And it can also forecast into the future at a number of different horizons. So what those horizons look like, you have the backwards horizon, and we can produce those historical records of flows as far back as the year 2000, which is when the satellites we use began sending down data to Earth. And so again, that can either fill in records that are spotty, where gauges kind of were intermittent, or it can fill in data where you have no information at all. We also provide a short-term forecast that's a 10-day horizon, and that is designed specifically for operational decision-making, and our accuracy there is very high. And we have a seasonal forecast as well that goes 6 or 12 months out, and that helps understand the year to come and plan around that year, and understand when streamflow, the timing of the streamflow throughout the year. So that's a little bit about the background of Hydro Forecast. I know I'm glossing over some pretty big topics of machine learning and satellite imagery and all that in just a couple slides, so we can come back to questions in a little bit. But with that, I'd like to hand it over to my colleague Laura, who will tell us a story using Hydro Forecast to understand better a basin and its relationship of snow to streamflow. So Laura, over to you.
All right, thanks, Marshall. So yeah, we thought it would be a fun way to get to know Hydro Forecast and the model and the services and value we can add by digging deep into a basin that we're providing forecasts at right now. And we are going to choose a basin that's in this Ciati Forecast Rodeo. I don't know, some of you may be familiar. It's a nationwide competition, and the basin that we'll talk about today is in the Trinity River in California. So not the Trinity River that I grew up in. I grew up in Texas near a very different Trinity River, but this one is in California. If you look on the map here, it's located in north central California, and we chose this site for a number of reasons. The California drought, it's particularly interesting to compare this year, which is atypically dry, with a normal year a couple years ago. So we'll dig into that, as well as just wanted to showcase how our model can do in a snowy basin. It's one of the features and places that we can show some good accuracy. So wanted to talk about that. A little bit about this basin before we dive into Hydro Forecast specifically. We're in the headwaters here of the Trinity River, and the story is that as water sort of collects in the Trinity Alps, it's a very beautiful area. I've backpacked on the PCT over here, and it is very Alp-like. The water kind of drains into the headwaters here and then passes down, flowing south. And if you can see in the satellite image, that's Trinity Lake, which is a Bureau of Rec project, from which a large portion, I've read up to 70% of the flow is diverted into the Central Valley project to provide for Sacramento River in all of its uses and stakeholders. Mount Shasta is what you see up in the top right here. And so the Shasta River parallels and also contributes to the Central Valley Project. So very, hydrologically interesting area, as well as important for most of Northern California and even down into Central California's water use. One other note, as we drain from Trinity Lake, the basin actually takes a U-turn to the northwest and continues into the Klamath River. So another sort of interesting hydrologically relevant basin as people talk about dam removal, restoration of natural flows, etc. So we thought this basin was interesting, and it was fun to learn about some of the history of mining here, logging after the mining industry left, then the loggers came in, and even a lot of the groups that are working on watershed protection and sort of Friends of the River are trying to understand how the roads, particularly that were built in this era of extraction, sort of led to destabilization of the banks, and they're sort of still trying to grapple with restoring that today. So an interesting basin to dig into. And we'll start with the story of snow. So I'm pulling a couple of images here of the basin. On the left, 2019, on the right, 2020. And these images were taken from MODIS on the same day of the year. So I believe it was like May 2nd. And white means more snow, and blue means no snow. And black means some issues with just something in the image. So if we think about the story that this can already start to tell, basically in May of each of these years, we see that there was more snow covering some of these higher altitudes in 2019 as there was this year. And so, when I see this, I think of a couple of questions of why, right? Was it that there just wasn't as much precipitation? Was it that temperatures melted the snow faster or earlier in the year? And the question we as hydrologists would ask is, what implications does this snowy states have on streamflow? And then as a manager or someone working as a user of this river, what does that mean for my allocation of that year? Or what does it mean for the fish that are going to be traveling up and down the river systems that this feeds, et cetera? And so if we dig into that a little bit, we'll start with the observed record. So 2019, we're showing April to July, and that's typically what some refer to as the freshet season, the snowmelt season, where the temperatures are warming. You're still getting some precipitation, so some of that can fall as snow, as rain, but you typically have this signature peak where flows go up and they can pulse a little bit and then they come down. And in 2019, just to put this year in context, this is a pretty typical year. It was drier than 2015 to 17, but it's much wetter than the last 2 years. And the drier years, 2011 was really dry, 2014 was really dry. So it's a little bit wetter, but not atypical wet. Now, if we look at how the last 2 years have played out, if you're looking for that spring pulse around April, which I'm always looking for, it's not really there. So this is the observation record from that USGS station that's at the bottom of the basin that we're showing. And if you're a water manager, if you're someone who's relying on those spring flows, this is really important, and it kind of sets the stage for the rest of the year. It is potentially a more difficult time of year to predict. The low flows are also, can be tricky to predict, but this is really, the freshet season is a time that sets the stage for many of the users and stakeholders on the river. So we're going to dig into that a bit more. Now, to otherwise contextualize this year with the historic record, we can add on the long-term median. So what this is taking the full historic observations from the USGS record, and for each day, what was the median flow, and then plotting that alongside the observation record. And so what we can notice here is, yes, 2019 was a bit wetter, and 2020 and 21 were a bit drier. So the next question is, with a model like HydroForecast, what's the added value? Because sometimes if you're not using a forecasting product or a model or something like that, the long-term median, or sometimes people say climatology, long-term average, a lot of people are using that as a predictor of the future. And sometimes that can work really well. In a time when we have, extremes and different years, even within the same basin, it can be not as great of a predictor as a model. And so to understand what hydro forecast can sort of layer on top of this information, I'll pull on our flows looking back over this period. And so looking closely here, the orange line is our mean prediction. It kind of follows the black line. It's a bit hard to see at some points. And then the blue bands are the confidence intervals, the 90% and the 50% confidence intervals that go along with the prediction. And so at every time step, hydro forecast is predicting the full probability distribution of flows. And that really is a helpful way for a group, because we have different users that are going to interpret risk differently. And so to be able to provide those confidence bounds gives a given user or customer a way to sort of apply their own risk bubble to the flows and use that confidence as they would to make whatever decisions they're going to make. So if we think about this, I want to dig in a bit to this freshet period. It's a bit hard to see when you're looking over multiple years. So I want to take 2019 and then 2021 on their own and just compare those. So here I'm showing just that same period, March to about July. And this is 2019, where we had that sort of signature pulsing happen that we would expect. And the top plot is a series of our 24-hour or 1 day ahead forecasts in orange compared with the observation in black. And so we did this by stacking together our forecasts for this period into a continuous line. And then the bottom is the 4 day ahead forecast. And so a couple things to point out here. One is that our forecast is able to capture not only the magnitude, but the pattern, even out to 4 days in this case, and longer. We're providing 1 to 10 day forecasts for this competition. The other thing is just the long-term median is under predicting for this particular year. And it's also, as we'd expect, it's very smooth. It's not able to really get the peaks, which are important for allocation and all the different uses, hydropower especially, being able to predict on the day ahead or week ahead markets. And now let's compare that to 2021. So just flipping back between these a bit, a couple of things to notice. First of all, the actual magnitude of the flows. So here we're looking at between 500 and 1,000 CFS, whereas in 2019, we're somewhere between 1,000 to 6,000 CFS. So, much different magnitude as we saw in that longer time series. And again, the model is really able to pick up on those more muted peaks, and the pattern and magnitude of that, even out to 4 days ahead, we're still within the 90% confidence bounds. And then again, we have sort of the flip situation where now the long-term median is over predicting the flow. And so if you're relying on that as a predictor, depending on what you're trying to use it for, that might give some trouble. And so I think, as a scientist like myself, a hydrologist, I'm asking why. How does the model know that this is happening? What are some of the things that it's learning to be able to predict in a wetter year, a typical wetter year, versus also a drier year within the same basin? And I'm just going to reiterate in a slightly different visual what Marshall had mentioned before. So we have this core model, and that core model is bringing in inputs from satellite observations. So we've got like SNODAS and MODIS and things that are telling us something about the land cover of the basin. Then any gauge measurements, they can be private gauges, USGS gauges, those come into our model as well, and they help teach the model as well as assimilate in real time. And then multiple weather forecasts. So we know that in a hydrologic model, usually the weather forecasts are a big part of the uncertainty and sometimes error in the forecast. And by providing multiple sources, we're able to help the model learn which forecast to trust under different conditions. And I'll just say one thing about the core model is that we're training this model over hundreds of basins, 400, 500, 600 basins. And so it actually sees more hydrology than a typical process-based model would, where you would take all the information you can for a basin, you would calibrate it, and then you'd validate it. This model is actually seeing many, many different hydrologies, and so it's able to learn patterns of hydrology and processes of hydrology rather than just, as Marshall was saying, the data from your particular basin. So that's one of the strengths and one of the big differences I've seen in working with this modeling framework and architecture versus a typical process model. So then we can make these predictions. And I think a way to understand why the model is predicting what it's predicting is to actually interrogate some of these inputs. So if we investigate these inputs, I want to start with snow on the left and vegetation on the right. And essentially what I plotted here are two different satellites, the MODIS snow cover and the NDVI vegetation index for both years of interest. So 2021 is in blue and 2019 is in orange. And again, zooming in over this period of interest from about March to June. So I'll just take a moment to sort of let folks orient around these patterns. And maybe it's as everyone would expect. As you move through the spring, snow cover is declining at some rate, and vegetation is increasing because essentially as the snow is melting, the ground is getting access to sunlight and water, which is what it needs to grow. And so we expect this. And these two things together is helping the model learn how to melt snow, how to turn it into runoff, all of the things that eventually end up impacting the stream flow. One interesting comparison here between the years is just if you drew a vertical line, let's say like May 1st, the difference in snow cover, as we saw in that original image on the map version, really in 2021, we're sitting at about 20% versus 2019, we're about 40%. So it's a huge difference. And the model understands how much snow is there and how that can sort of impact stream flow. At the same time, if you look at the vegetation, that story makes sense because in 2021, we were greening up much earlier and at a much higher, we're already starting at a higher rate, so there wasn't as much snow to begin with. And that has a lot of impacts, and it really does guide hydrologic processes because as the soil is drying out earlier, like if it greens up faster, the soil could dry out faster if there's not a lot of rain. And that can increase wildfire risk, and drier conditions within the basin. So it's really important for some of those habitat or sort of groups that are concerned not only about the amount of flow in the water, but just about the overall protection and states of the watershed. So I think this is one story, and then I would ask myself or ask, well, why is there less snow? Why did the snow melt? Was it these temperatures? Was it just not enough snow or not as much snow? And so to answer that, we can also include plots like temperature and precipitation. And so all of this, if you were to be a customer of HydroForecast, essentially you would receive a dashboard which has all of these inputs and their time series plotted for you to understand how these inputs are impacting the stream flow and why the model is doing what it's doing. So here I'm plotting the temperature and precip from the ECMWF. I just picked one because it makes the plot a little less busy. But from about March to mid-June of this, of both years, 2019 in orange and 2021 in blue. And just a few things to note here. So this is the 0 degree line. So below here is freezing and everything above here in Celsius is above freezing. And a couple of things I noticed in 2021 and early April, it's just a little bit warmer earlier here, sustained warmth. So it could be melting that snow. And then again in May, it's just warmer. The temperatures are just warmer at the end of May than they were in 2019. And so how does that sort of also influence the precipitation story? Here, I'm just accumulating the millimeters of precipitation that occurred from December all the way to June in both years. And there just wasn't as much precipitation this year as there was in 2019. And so with all of those things together, we can kind of put together, why the model was able to learn and predict very well the patterns, the very different patterns that occurred in these 2 years. And aside from qualitative assessment, because we're doing these live forecasts for the rodeo, for the CID forecast competition, we're continuously calculating metrics. So we wanted to just understand how our forecasts are doing compared to the NOAA products that are available, both the RFC forecasts and the National Water Model, as well as just if you took the long-term median. And essentially looking out over the available horizons, so the short horizon 1 to 3 days, all the way out 6 to 10 days, and then overall 1 to 10 days. The metric we're plotting here is Nash-Sutcliffe efficiency, which is a common hydrologic metric that's measuring the agreement between the model and the observation. And really, hydro forecast out at these later horizons is able to keep its accurate predictability way higher than a lot of the other options. And we see this at different basins across the US. And I think it's because of how we're able to provide it a range of inputs that are flexible. And so the model can learn these behaviors and keep that information all the way through to a longer horizon. And so as a manager, it's interesting to think about what this extra time period of having confident and accurate predictions can get you. And depending on what industry someone might be coming from, those are different benefits. Basically, last slide here, I'm just wanted to reiterate, like, why are we doing this? I think, for us, providing a product and a model that can help with critical decisions within a basin. So, if you're trying to manage this river system, we need a product or a model that's flexible, able to capture both a dry year and a wet year. And in this case, we have a lot of decisions that are happening on these 1 to 10 day horizons. Like, I have heard that California will be trucking salmon from the rivers to the ocean and back. And so to get people out in a week's notice, if you know what the flows are going to be like, we're really interested in helping to provide information, decision support tools for all of the different users, stakeholders that interact and are working with these rivers. So with that, I will stop and see about discussion.
So I imagine folks are probably saturated with Zoom these days, but just as a quick reminder, if you do have any questions, at the bottom of your screen, there's a little Q&A button that you can click and submit to add them to the conversation.
I see a question. So where does the model work? So Laura, is it specific to certain geographies? Does it require new work for new geographies? How does that process work?
Yeah, great question. So we are forecasting at different locations and basins across the US, actually North America, and also in Europe. And so because of how we, going back to that core model, because of how we train the data so that the model can see many different types of hydrology in different geographies and different alteration situations, snow versus rain driven, essentially the model can work in any of those conditions, small basin, large basin. And then what we do from that core model is take any of localized information, gauge data, et cetera, and tune the model so that we can understand its behavior and get the parameters correct and more accurate for the specific location.
Yeah, so just to put that in other words, like we've basically trained a machine learning model to produce forecasts anywhere. And we've provided it with so many different scenarios that it is able to generalize and produce really reliable, ungauged forecasts anywhere. And then we can tune it for a specific basin to make it even more accurate if there's additional customer or private information about Streamflow. But that's a great question and something that really sets hydro forecast apart. Here's another great question. Does the model address reservoir diversions and other features that are human-driven flow modifiers? Laura, do you want to take that? I know that's an area of your active work.
Sure. Yeah, I can start. You can jump in. So great question. And the short answer is yes. We have tested this on the state of California. So we're working with the Nature Conservancy of California to understand how our model can predict in altered basins, so ones that are not headwaters and nice and pretty, but in places where there are multiple uses such as reservoirs, irrigation, etc. And we've worked on a model across California, about 300 basins. And we're able to get really nice predictions, even in places that had a dam or multiple reservoirs upstream. And we did that by including what we call enhanced basin characteristics. So data sets that have channel alteration, stream cat, which is an EPA data set, and things like that. We haven't yet incorporated like operator real-time release information, partially because then that takes away from the scalability of the approach, and also because that data is very difficult to get and messy and all of that. However, if we had that information, if we knew the reservoir releases, it would certainly be something we could incorporate and make the model even better.
And then one bit I'll just add to that is that the satellite inputs actually tell you a lot about the landscape as well, especially in places where there's a ton of agriculture, for example. And so we found that vegetation index that we take from the satellite, NASA satellite called the MODIS constellation, the vegetation index is also reflective of the timing and intensity of that year's agriculture, and that can really help us. That's a coarse proxy for amount of water used for ag, but actually it does help the model in many ways. Here's another question. Can you forecast on different horizons beyond 1 to 4 days?
Yeah, absolutely. And if we go back, well, let's see if I can go back. I think we provided a summary of that. But yeah, so right now we have essentially 2 different horizons. We have a 1 to 10 day model, and that's an hourly model. We can also aggregate those predictions to daily predictions, and that's for short-term kind of operational decisions, and that's integrating certain weather products. And then we also have the seasonal approach, and on that seasonal model, we can go 60 days, 90 days, all the way out to a year. And we've actually seen quite good results from our customers on that seasonal approach. And that, of course, is actually integrating, I'll just say, different inputs. It's integrating some weather information, but also climate indices like the INSO and some of those cycles that are a bit longer term. We're integrating information about those as well.
One more question for you. How does hydro forecast handle climate change and changes within a basin?
Great question. So 2 parts to that. The first one would be, because we're pulling in near real-time basin conditions from the MODIS satellite. So like, let's say there was a wildfire that occurs in the basin. Essentially, the model is already picking that up because it is pulling vegetation and all of the different land cover data sets as they're available. And so we actually get to skip a step where if you're a process model, you need to go back, recalibrate after that change, and do everything again, because the model is just naturally able to pick up on that change that's occurring and learn that. On the climate side, like future climate side, we are interested in sort of adding another bucket to this product list. And we've heard that would be useful for longer term planning. And so we've got some R&D in the works to understand the use case and what type of value we could add to that. But it'd be, if you're whoever's asking the question, if you're willing to send us an email later, it'd be great to understand the use case for what types of decisions you would use for that.
Another here, what is the time step and can it be varied?
Yeah, great. So on the short-term model, we have an hourly time step, and that would be out for 10 days. We can also aggregate to daily, so we can provide a daily forecast out to 10 days. On the seasonal, it's a bit flexible. In some cases, we can provide daily estimates for the first, say, 30 days, and then we provide monthly estimates. We could also explore weekly in there, but out to, if you're looking 7 to 12 months ahead, really a monthly distribution is as comfortable as we feel with the fidelity of the information available.
Awesome. I am not seeing any other questions, but those were fantastic ones. So thank you for the folks who sent questions in. I think with that, we can wrap a few minutes early. If you have any questions, Laura, could you go to the last slide? You can quickly commit to memory this email address, which is also available on the website. So if you go to hydroforecast.com, you could see how to contact us. But yeah, we'd love to hear about how you are making decisions in river basins, how we could be helpful if in any way. And yeah, we'll follow up with the recording if any of your colleagues would find this useful. And thanks for joining. Zoom will not let me turn my video on, but I am waving and smiling. So thank you all.
Thanks, everyone.